Okay, so today we'll start discussions from second law of thermodynamics. Okay. Give me a moment. I will directly show you from the book. I'm trying to find it in the book. Just give me a moment. Second law of thermodynamics. Zeroth law. Okay. So how many of you are there? Okay, we are three people, so we can start. Okay, so good morning, and we are going to start with the basics of second law of thermodynamics. Okay, I mean, last class we discussed about work done during an adiabatic process. I hope that was clear to you. Today I will give you the notes, and yeah, later after this class, the note I will give to you. Okay, so second law of thermodynamics. So we have finished first law of thermodynamics. Now moving to second law. And first law of thermodynamics has some limitations, and that's why we have to go to another law of thermodynamics called second law. Maybe in one of the slides I have mentioned what are the limitations of the first law. Well, okay, one of the limitations of the first law of thermodynamics is that it does not tell us about the direction of flow of heat. Like heat will flow from high temperature to low temperature, or low temperature to high temperature, or in which direction it will flow. Okay, and okay, I can share the PowerPoint with you. Yeah, here you can see. So here I have taken some important points from internet. So So limitations of the first law. We have finished first law of thermodynamics, but it comes with certain limitations. One of the limitations is it cannot give us the direction of heat flow. No, like heat flows from low temperature to high temperature to low temperature. Whether we have to do some work for heat to make flow, or we don't have to work, or a body can spontaneously take it from a high temperature to low temperature, or low temperature to high temperature. So these things are not easily not cannot be explained by the first law of thermodynamics. Okay, and another big disadvantage of first law of thermodynamics is this one. This point, point 3, amount of heat converted to work in and vice versa. So suppose you have applied certain amount of heat to a system. So what amount of that heat will get converted to work? Will all the heat get converted to work, or will all the work that you get that will get converted to heat, and vice versa? So these things are not very much clear from first law of thermodynamics. Okay, so in one sometime we learn that okay where can I go to the equation of first of thermodynamics. Okay, so in this equation from first law, first of thermodynamics, so if now this heat can be equal to work done when internal energy is zero. Okay, but when you are supplying heat to a system, can the internal energy be really zero? No, the internal energy cannot be zero because internal energy involves potential energy and kinetic energy. So if you supply heat, so the molecules will get kinetic energy, okay? And if they get kinetic energy, their total internal energy will increase. Therefore, delta U term actually cannot be zero. So in that case, the total amount of heat which you are supplying to the system cannot be converted to work, okay? So that is a limitation of first law of thermodynamics. Limitation means one of the limitations. Okay, so where were we? Okay, yeah. An insufficient condition for the process to occur, like under which condition it can occur. It will occur in isothermal process or adiabatic process, or under what condition this conversion of work into heat or heat into work will occur. Okay. Okay, so I think I will stop the share here of this PowerPoint, and I am going to the book. Let me share. Yeah, I think you were seeing this second law of thermodynamics. So in your syllabus, these things are there where a reversible process, irreversible process. Okay, then what are the examples of reversible and irreversible processes? What are the conditions? So these things are actually there, and actually I have the notes, no, all because last semester, I mean 1 year back also I taught this course to your seniors, and I have all the notes. But because before no, because the notes are there in my room, at my room in Guwahati. So and since lockdown started, I have not been able to go there, so I am not able to access the notes. But most of the notes I made from here. Okay. So I don't. If I am able to go back, then it will be very easy for me to supply you the notes. Or slowly, I will keep on adding the notes. Okay. Okay. So some basic things today I'll discuss directly from the book. So I suggest all of you to take pen and paper with you, and so that you can make some important points. Okay. Okay, so reversible process, irreversible process. So very important concepts of thermodynamics, reversible process. Okay. Okay. So let me read the definition first, and then we go to the details. Okay. So here is the definition at the last line of this paragraph. So a reversible process is that which can be retraced in the opposite direction, so that the working substance passes through exactly the same condition as it does in the direct process. Okay, reversible means like suppose okay, maybe I will give you some annotation. Maybe it's given somewhere. Yeah, so here what is the topic? Cyclic process. So here this one I can show you. So this process you can see, so this is the initial state of a gas. Suppose the gas is initially at pressure P1 and a volume V1, and then finally the gas reaches a state P2 V2. Okay, and A is the initial state and B is the final state. Okay, so the gas suppose changes from A to B via the path E. Okay, AEB. So between A and B there will be various values of pressure and volume. Okay, you can see along x-axis there is volume, along y-axis there is pressure. Okay, Now A to B, okay, the gas reaches the state B from the state A, okay. But now if you do something with the gas may also be taken back from the uh, state B to the state A. At state B, the gas is having these pressures and volume, this P2, V2, and after some physical or chemical changes, the gas moves back to the initial state of A, okay, where the pressure and volume are P1 and V1, okay. Uh, so this is the like a reversible process. Reversible means you can reverse the state of the process. Okay, A to B and B to A, and from A to B, whatever steps were followed, whatever steps or stages were followed in the transformation of state from A to B. Similar steps will also be followed from the transformation of the gas from the state B to state A. Okay, A to B, B to A. Similar states are followed. So such processes are reversible processes. Okay. So here the topic is a bit different, the figure topic, but by definition, this can be a reversible process. So some examples are given. Okay, let me just read it. I'll not explain that much. Consider a gas enclosed in a cylinder fitted with a frictionless piston. Okay, why frictionless? Because if there is friction, so some no energy will be lost during heating. Okay, and for a process to be reversible, we don't want any energy loss. Okay, therefore it is assumed that the piston itself is frictionless, perfectly insulated from its surroundings so that no heat can leave or enter it. Okay, the gas is kept in a cylinder and insulated from its surrounding. Some removable weights are placed on the top of the piston. Okay, some removable weights. No, you put some weight. Why? Suppose the piston is like this. You put some weight, and the piston will actually come down. Okay, the gas will be compressed by some amount. Anyway, so P1, V1, T1 are the pressure, volume, and temperature of the cylinder in the initial state. Okay. So initially the gas will be in a state where the pressure, volume and temperature values are given by this P1, V1, T1. Okay. Okay. Now initially this P1, V1, T1 are the pressure, volume, temperature when you have already put the weights on the gases. Okay. Now what you will do? You will remove the weights. Okay, now the weights of the removed by very small amount at a time. Okay, so one weight you remove, then the other one, very small amount, not suddenly, not all on a sudden, or not by huge amount, not huge amount of weight, but you remove the weights one by one very slowly. Okay, at a time, so that the piston moves outward very slowly. Okay, the piston has to move outward. So initially this is the position. Can you see my both hands? Initially this is the position, but you remove the weights. If you remove the weights, the piston will remove very slowly. Okay, the piston will remove very slowly upward, very slowly. Therefore it not even very, but very slowly. It is written here. You can see two very words are used. The gas now expands adiabatically, and the pressure and the volume of the gas adjust themselves so that the system is always in thermal equilibrium. Okay, so we are adiabatic because the gas is placed in a cylinder which does not allow entry or exit of heat, entry of heat to the system or exit of heat from the system. Okay, so this process is actually adiabatic that we have considered somewhere here, perfectly insulated from its surrounding. That means no heat can pass, and the gas now expands adiabatically. Okay, the pressure and volume of the gas. Okay, but at the same time, thermal equilibrium is maintained. Okay, so the piston moves very slowly, very slowly. If you can see my upper hand, why? So that there is no temperature difference. Of course, the gas volume and pressure will change, but no temperature difference. Why? In order to maintain thermal equilibrium. And this is only possible if the piston expands very slowly, very, very slowly. In other words, adiabatic expansion of the gas is quasi-static. Quasi-static means like very small, a very slow process. Okay, adiabatic expansion means the gas expands, but the process is like very, very slow. The process of removing weights in small steps is continued so that P2, V2 pressure, volume, temperature of the gas in the final state. Okay, so the process of removing the weights. So you remove all the weights and after you have removed all the weights, the piston will move to a new position. And suppose at that new position, the pressure, volume and temperature of the gas are given respectively by these values which are P2, V2 and T2. Okay. So initially, the gas was at P1, V1, T1 when we placed weights on the piston. But later we started removing the weights very slowly, very slowly, and finally the gas reaches a state where pressure, volume, and temperature values are given by P2, V2, and T2. Okay, in the final state. Okay, so yeah. The weights are now replaced again in very small amount in a time so that the piston moves inward very slowly. Okay, so again the gas moves from initial. Okay, maybe I can annotate something. Just give me a moment. So suppose A and B are the two different states. Okay, so initially the gas was at this state and then we have reached a state. So at state A, we have pressure, volume, temperature as P1, V1, T1. And at state B, the pressure, volume and temperature are like P2, V2 and T2. Okay. But now the weights are again placed. You have again placed weights on the piston so that the piston again starts to move very slowly. Okay. So now you start compressing the gas. So when the piston moves outward, the gas expands. We know this, and when the piston moves inward, the gas compresses. Okay, compress means the reduction in volume. Okay, so the compression of the gas is also quasi-static. Quasi-static means a process which is very small. Or maybe quickly we can see the meaning of the word quasi-static. So quasi-static, quasi-static process. Okay, from Wikipedia, the definition of quasi-static means a quasi-static process is a thermodynamic process that happens slowly enough for the system to remain in internal equilibrium. A reversible process is quasi-static. So I hope you have understood by now. The quasi-static process has to take place very slowly so that thermal or internal equilibrium is maintained. So that is the quasi-static process. Okay, very slow. Okay, so the process of replacing the weights in small steps is continued till the gas reaches the initial state P1, V1, T1. Okay, so you started putting the weights on the what is this called, on the piston. and again the compression of the gas happens, and we get these values of pressure, volume, and temperature P1, V1, and T1. Okay. During this process, adiabatic compression of the gas would pass through exactly the same intermediate steps through which it passed during the adiabatic expansion. Okay. So initially we have done adiabatic expansion by removing the waste. Okay. And then followed by this we have done adiabatic compression. Okay, very slowly. So the steps which were involved in adiabatic expansion will be same as the steps involved in adiabatic compression. Okay, so this is what written: during the process adiabatic compression the gas would pass through exactly the same intermediate steps through which it passed during the adiabatic expansion. So expansion and compression will involve the same steps. Okay, that is, all the intermediate states are retraced in the opposite direction. Such a process is known as a reversible process. So what is a reversible? A reversible process is that which can be retraced in the opposite direction. Okay, you can like in the figure I have shown you, going from A to B and then again from B to A. So it involves the same steps, no? And such processes are reversible processes. Okay. So then I hope by now you have understood what are reversible thermodynamic processes. So they have to be very like no very slowly performed. The process like no change of state from one to another should be very small, and yeah, the change should be very small. And what else? And the change from one state to another should involve the same steps in the otherwise in the opposite direction too. So okay, so maybe I can annotate quickly. So A to B, A to B, A state to B state, then again from B state to A state, they involve the same steps. Okay, same steps, and in that case, the process will be termed as a reversible process. Okay. So now condition of reversible process. So what are the conditions? The first condition for a process to be reversible is the process should be carried out very slowly, very slowly, so that the system remains in thermodynamic equilibrium in each stage of the process. Okay, very slow process, and the system must maintain thermal equilibrium. That means the temperature of the system should not change. Okay, or the process is quasi-static. Same quasi-static means the process has to be carried out so slowly that it always remains in equilibrium. There should be no frictional forces present. The frictional forces, if why no frictional force should be present? If there is a frictional force, in that case, some heat or energy will be some energy will be lost due to heating. And if that happens, then the gas will not be in any equilibrium, no? Because when heat is involved, so there will be change in temperature, and change in temperature means there would not be any thermal equilibrium. Okay, so that is the reason the friction should not be present. And whenever we consider that we have a piston, and the piston was considered to be frictionless, if it had friction, in that case what would happen? Heat would be lost, and if heat gets lost, temperature gets changed, and the process would no more be in equilibrium. Okay, I hope this is clear. Okay, so some examples of reversible processes are given. Reversible processes are actually very difficult to observe, but still we have some examples. Like, okay, all isothermal and adiabatic changes are reversible when performed slowly. In such a case, there is no friction. It is assumed that there is no friction to overcome, and work is done in overcoming the friction to no, what is it? In such a case, it is assumed that there is no friction to be overcome, as work done in overcoming friction is wasted. Okay, yeah. So the process carried out is very slow. No heat energy is wasted, producing oscillations and eddy current, etc., etc. Okay, and no heat is lost by conduction or convection radiation. Okay, so no work should be done against friction, and no heat should be lost by any one of these heat conduction mechanisms. Okay, so the processes have to maybe isothermal and adiabatic, but they have to be carried out very slow. Okay, so and one example, ice melts when a certain amount of heat is absorbed. The water is formed when converted into ice if the same amount of heat is removed from it. Okay, so reversible process, one very good example is that the conversion of ice into water and water to ice. Okay, so this is a reversible process. So ice is a solid form and water is a liquid form. So ice to liquid you can get when you apply certain amount of heat. No? When ice melts when certain amount of heat is absorbed by it. When ice absorbs certain amount of heat, it melts to water. And when you remove some heat from water, then what happens? Water gets converted to ice. So this is a very well known reversible process. Okay. Okay. Then this Peltier effect, thermocouple Peltier effect example is given. Then electrolysis is also another example of reversible process. Okay, so is this concept of, so these are some examples, like if the resistance of a thermocouple, then no heat is produced due to Joule heating, Peltier heating or cooling reversible. Okay, so this is another thing, this thermocouple thing, and electrolysis. Okay, so now have you understood more or less what is a reversible process? Because next we are going to learn about irreversible processes. So in nature, actually, most of the processes are irreversible. Okay, I mean you cannot go back to the previous state. Once you have changed the state of the material, you cannot go back to the previous state. Yeah. Okay, I'll take some water quickly. Okay, irreversible. Okay, so in reversible processes, so when we were removing the weights from the piston, or where we are replacing the weights to the piston, in that case, what we consider that this removing and placing of the weights were carried out very slowly. Okay, very slowly. But in irreversible process, the same thing we do, but if you do it quickly, quite quickly, okay, the gas will undergo sudden expansion, and so that the intermediate states will not be in equilibrium. That is, it is not possible to define a value of pressure, volume, temperature for these states. Okay, suppose uh, suppose you have a piston, and instead of removing it very slowly, you remove it all on a sudden. Okay, you remove the piston all on a sudden. In that case, there will be no definite values of pressure, volume and temperature during the expansion. Similarly, if you press the piston very quickly, okay, compress the piston very quickly, in that case also there will not be any fixed values of pressure, temperature and volume. Okay, so the gas will undergo quick or sudden compression or expansion of expansion. Therefore, pressure, volume, and temperature things will be very difficult to measure, and will not be very well defined. Okay. During the process of sudden compression, it will not be possible to reproduce the intermediate states through which pass through through which the system passed during sudden expansion. Okay, such processes are irreversible processes. Okay, so the definition is here. Hence, an irreversible process is that which cannot be retraced in the opposite direction, so that the working substance does not pass through the same intermediate states through which it passes during the direct process. So, from direct process, like from when we change from A to B, so whatever the intermediate steps are due to in sudden expansion from A to B, whatever the intermediate steps are involved, those intermediate states will not be reproducible, if you move from the state B to A. So state A to B, different sets of values, state B to A, another set of values of pressure and volume. Why? Because the process is very sudden and the intermediate states will not be in equilibrium. The intermediate states will not be in equilibrium. Okay, so it is very difficult to define their pressure, volume and temperature values. Okay, so this is just the opposite of reversible. If you understand the reversible process, so it is very so irreversible processes are very easily understood. Okay, if you know well the definition of reversible process, you can easily define an irreversible process. So some examples are there. No, work done against friction is irreversible. Friction, no, because always some heat is lost during friction. It is because reversible. In reversible, the direction of motion against again work done has to be against friction. Okay, so from A to B, suppose you are moving from A to B, if you have to do some work against friction, then again when coming back from B to A, you will again have to do additional amount of work against friction. So you are doing, friction you have to encounter two times, and if you have to encounter friction two times, then the initial state will not be same as the previous state. I mean, first time your heat will be lost, second time also your heat will be lost. Okay, so or heat will be involved, and therefore this process will not be in any thermal equilibrium. Okay, so if friction is present, work done against friction, heat will be lost, work will be lost in heat as heat. And if it happens both times means from A to B and then from B back to A, then two times you are losing heat, and in that case the process will not be in thermal equilibrium and it will be an irreversible process. Okay, then Joule Kelvin effect. Okay, this is different. Then rusting of iron. No, you know rusting of iron. So if one once rust gets in iron, so it is impossible to get the pure iron back. Again, heat is produced by passage of current through resistance is irreversible. It is because even when the current is reversed, the same effect is observed. Okay, because heat is generated now when current flows through a conductor or a resistance, and again if current has to flow in the opposite direction, then again heat will be produced because of the passage of the current. So under these circumstances, the flow of current through a conductor or resistance is an irreversible process. Okay, so that was all about reversible and irreversible processes. Okay, so this is included in your syllabus. I hope this is clear to you. Okay, next let us see what we can learn. Indicator diagram. Indicator diagram is like this. Now pressure, volume here, pressure here. Then at A step there is one value of pressure and volume P1, V1. B step is P2, V2. So what is an indicator diagram? It is a curve representing the state of a system by a points on a PV plane is called the indicator diagram. PV plane means pressure volume plane. Okay, that is a indicator diagram or PV diagram. Okay. So importance of PV diagram, already we have for even we have done this work done during isothermal process or work done during an adiabatic process. So we have already seen similar curves. The importance of PV diagram lies in the fact that the work done by the gas during the expansion from volume V1 to volume V2 is given by the area of the PV curve. So work done is PdV, and when you do the integration from V1 to V2, okay. So this area, okay, let me annotate. So so in such a PV process, like now in a PV diagram, which quantity gives you the work done? The area included in the by the PV curve and the V axis. This is the PV curve and this is the V axis. V axis is volume axis. So this portion, okay, I have to actually cover whole of this, but I don't know if I can cover or not. Okay, if someone likes to paint, can keep on doing this slowly, slowly. Yeah, anyone likes to paint?
Raihan.
Oh, really? Yeah, yeah, yeah. He told me that he likes to paint. Huh, Raihan? Yeah, so now Raihan, you tell me, how is my painting? Yeah. Does it look bad?
Good, very good, sir.
Yeah, very good. You were flattering or you were serious?
No, no, sir. Really, it's very good.
Okay, if you have complimented, then I think I am really a good painter. No?
Yes, sir. You are, sir.
Yeah, thank you. Okay, anyway, so my intention was not to paint here, but just to show you that whatever is written here now. So whenever you have a this no this type of figure with PV diagram, volume along the x-axis, pressure along the y-axis, and there will be a PV graph like this. PV graph means which was pressure against volume. So when we know that when volume increases, pressure decreases. So initially pressure was P1 here, but now with the increase in volume, pressure is decreasing. Pressure volume is here P2, no? Because pressure is along the y-axis, and this area enclosed between the volume axis and this PV diagram is the work done during the process. Okay, because when we have learned about isothermal expansion, work done during isothermal expansion or adiabatic expansion, in that case we also learned that no, this area gives us the value of the work done. Okay, so I hope you will never forget this. I'm removing the annotation. Okay, now let me see where I can go. Okay, this is not required. Cyclic process. Cyclic process is there in your okay, whatever. I think no problem, no harm in learning it. So, what is a cyclic process? So, a cyclic process is a thermodynamic process in which the system returns to its initial state after undergoing a series of changes. So, here, so it is initially at A, then it goes to B via the path A B, then it again returns back to the state A via the path BFN. Okay, so this type of processes are cyclic processes. Closed cycle is like now A E B no A E B D C A. This is a closed cycle. So everything they work done, no work done they have taken to be this, and work done W2. In that case, it is B D C A F B. Okay, that is work done during compression. So what is the work done in the cyclic process? It will be your W1 minus W2. Yeah. So let me try to recall. Do you really need this? Okay, in 2 minutes I can explain. I think it is not in the syllabus, but maybe you should learn it. Okay? Just quickly, because we have many more important things to learn from second law of thermodynamics than learning now. So of course we will come to those things. So this is a cyclic process, A to B, B to A. Okay. So now what is the work done during the cyclic process? How will you calculate the work done? So the transition is not along the same path, but it is along two different paths. So when there is expansion, expansion means the volume is increasing from C to D. C and D are nothing but volume values, no? Because you see the volume is plotted along the x-axis and the pressure is plotted along the y-axis. Okay. So from where we are, when we are moving from A to B, there is an increase in volume from V1 to V2. But then we again perform a process back from B to A through the path BFE, and the volume decreases from V2 to V1. Okay. So now in such a process, what is the work done? So what is the work done? Okay, instead of reading here, I will explain in the figure. So in the first case, the work done from A to B through AEB. Okay. In that case, the work done is whole of this area. A, E, B, D, C, A. So whole of this, just now I have explained that the area under the PV curve or PV diagram gives you the work done. Okay. From A to B, it happens through AEB, and the whole of this area, that paint I had shown you earlier, that gives the work done. But now what is the work done when we have to move from B back to A via the path of BFA? In that case, the work done will be AFB, or not so AFB, that is given as BD. Yeah, AFB, but let me go it from B. B, D, C, A, F, B. We start from B and again we like B, D, C, A, F, B. Initially it was A to, so when it was from A to B, we had to move through E. But when we are moving from B to A, we have to move through this, okay, BFA, and we do not consider the upper part of BFA curve. Okay. Okay, then that work done is suppose given by W2. W2 is the work done in moving from B to A. A to B work done is W1 here, and B to A is work done W2. Okay. So now, so have you understood this? Because just now, some moments back, I explained what is the work done in a PV diagram. Okay. Now, then what is the net work done? What is the net work done from A to B and B to A? The net work done is W1 minus W2. So what is W1? W1 is A, E, B, D, C, A. W2 is A, F, B, D, C, A. So if you subtract the second one from the first one, we will be only left with this area. That area is AEBFA. So AEBFA will give you, so here is the AEBFA. Why these things are coming? No, this is a bit disturbing. AEBFA will give you the net work done in this cyclic process. What is the cyclic process? You move from A to B and you move back from B to A. Okay, so this region gives the, so AEBFA gives you the net work done in the cyclic process. Okay, so you have understood. So W1 is equal to W is equal to W1 minus W2, and W is AEBFA, W1 is AEBDCA, and W2 is AFBDCA or BDCAFB. Okay, I hope this is clear. Okay, I think I am not going further. In the next class, we will learn about various statements. So Carnot cycle is very important. We will come back to this, and we will learn about the statements of second law of thermodynamics. Okay. So I'm stopping the share and also the recording.